For chapter 19, we're going to be switching gears here and talking about electrochemistry. So, in order to talk about electrochemistry, we need to review oxidation reduction reactions. So you might want to go back to chapter 4, look at oxidation reduction, look at oxidation rules, how you can tell if something's oxidized, how you can tell if something's reduced. We also, at the time, learned how to do the half reaction method for balancing a simple oxidation reduction reaction. And so you might want to go back and review that. So let's just review a little bit. Oxidation reduction reactions always involved a transfer of electrons from one species to another. The species that loses the electrons is being oxidized, and the species that gains electrons is being reduced. So oxidation is loss, reduction is gain. So when we have a redox reaction, then there's a transfer of electrons from the thing being oxidized to the thing being reduced. Now we also use some other terminology. If we have an oxidizing agent, it's actually the species that oxidizes something else. So it itself is reduced. So the thing that is being reduced is called the oxidizing agent. And the thing that is being oxidized is called the reducing agent because it allows something else to reduce. So just keep that in mind. So if we're looking at this reaction, let's just review a little bit. Iron, let's look at what are the oxidation numbers. First of all, the iron on the left has no charge, so it has an oxidation state of 0. Copper 2 plus has an oxidation number of +2. Oxidation state, oxidation number mean the same thing. Iron +2 has an oxidation number of +2, and copper without a charge has an oxidation number of 0. So if we look, we see that iron goes from 0 to +2. It's losing electrons. It's becoming more positive, so it is being oxidized. The copper ion, copper +2, is gaining electrons. The oxidation number is going down from +2 to 0, so it is being reduced. So, iron is being oxidized. It's lost 2 electrons, and so iron is the reducing agent. Copper +2 is being reduced by gaining 2 electrons, and so it is the oxidizing agent. So in this chapter, now earlier when we talked about oxidation reduction, we showed an example. If you put, like, say, a piece of zinc into a copper solution, that zinc will start to turn black. A reaction will take place. But what we're going to do now is separate the two half reactions, physically separate them into two different half cells. We call them, two different places, connect them with a wire, and then when the electrons flow through, we can have we can collect that electricity or the energy and use it. Okay, so the force with which electrons travel from oxidation half reaction to reduction half reaction is measured as voltage. We'll talk more about that later, but voltage, you've probably heard about that. That's the electrons moving, and that's what gives us the energy we can use. And then you might want to review the rules back in chapter 4 concerning oxidation numbers, and then also balancing really simple oxidation reduction reactions. So here is just a little bit of a review of oxidation numbers. Remember that elements, when they're in their elemental form, always equal 0. If there's only one element around, or even if there's more than one, if the total charge is 0 and there's only one type of element, its oxidation number has to also be 0. So I think this is the number one thing that students forget. Elements in their normal state, all by themselves, it could be something like H2 or Cl2 or whatever, their oxidation number is 0. Monoatomic ions are have an oxidation number equal to their charge. And especially, so if you see an ion by itself, it's equal to its charge. And just keep in mind, sometimes you'll see compounds with group 1A and 2A metals. And they are always, since group 1A metals are always a +1 and group 2A metals are always a +2, if they're in a compound, you can assume that those are their charges. Some of the others we can't always assume, but group 1A and group 2A you can pretty much remember +1 and +2. Now, oxygen. Oxygen is always a -2 in compounds. Almost always, I should say. Almost always a -2 oxidation number if it's in a compound. Remember, if it's by itself, O2 has an oxidation number of 0 because that's the element. But if it's in a compound, it's almost always -2. The exception is that every once in a while it might be a -1 if it's in a peroxide. Now, you can pretty much always assume it's a -2. The only time that you might question it is if you use -2, but the other numbers following the other rules get messed up. So if, for example, H2O2, if you said, oh, well, O is a -2, there's 2 of them, so that's -4. That means each hydrogen is a +2. Well, that can't be, because as you'll see in the next rule, hydrogen can't ever be anything but a +1 or a -1 in compounds. So the -2 kind of negates the other rule that hydrogen has to be a +1. So in that case, oxygen can be a -1. But I just want to point that out, that almost always it's a -2. All right, hydrogen, like I just said, the oxidation number for hydrogen in compounds is either a +1 in most compounds, unless it's paired with a metal, in which case it's a -1. So if it's paired, like if you've got NaH, Na is a +1, H will be a -1. But H almost always is a +1, but sometimes a -1. Again, don't forget, hydrogen in its elemental form, H2, will have an oxidation number of 0. Halogens, almost always fluorine is a -1. Other halogens are often -1, but if they appear in a compound that have other halogens or have other oxygen, involved, they may be other numbers. So fluorine always a -1. Halogens are -1 unless there's other halogens or oxygen around. Then you have to figure out what it is. And then the final rule is that compounds and ions, always the total sum, the sum of all the oxidation numbers of any compound is equal to 0 if it's if there is no charge on the, if it's a neutral compound, the total is equal to 0. If you have an ion, a polyatomic ion, the charge will always equal the total charge of the ion. So again, go back and review those back in, I think, the review sheet for this chapter, and the study guide will have some, and then we'll have some problems where you figure out the oxidation numbers, and there's also an extra worksheet for figuring out oxidation numbers, just for a review, but you might want to go back again and check chapter 4. All right, so like I was saying earlier, because the conservation of mass, when we balance a chemical equation, we always make sure that we have the same number of elements on each side, right? So you want 2 oxygen on each side, or 3 hydrogen, or whatever. But keep in mind, when you have a redox reaction, you still have to have the number of elements be the same on both sides, but the charge has to be the same on both sides as well. So we have to balance electron gain and loss. We can't lose more electrons than we gain. They have to be the same. So we have some specific rules for balancing redox reactions. And like I said earlier, back in chapter 4, we did some simple redox reactions. But we also have some more complex redox reactions that we're going to do in this chapter, and especially if it occurs in acid or base solution. So that's what we're going to do next. So if you're wanting to balance, and actually this method will also work for the very simple ones that we did in chapter 4. So this is just expanding and adding a little bit to it. If you have a very simple one, these rules will also work. Some of them won't apply, and you'll just skip them. All right, so if you look at a redox reaction and you want to balance it, we have to look at the main equation. So if we look at the main equation, or if I say here's this going to this, figure out first of all what's being oxidized and what's being reduced. Figure out what the products are of that oxidation and reduction, and those generally will be given to you. But that you might have to add a few other things. And then you also want to know, does the reaction occur in acid or base solution? All right, so let's look at the following redox reaction. Zinc plus hydrogen gives us hydrogen ion gives us zinc ion plus hydrogen gas. All right, so the first thing you want to do is determine what's being oxidized and what's being reduced. The easiest way to do that is by looking at how oxidation numbers change throughout the reaction. So zinc by itself with no charge has a 0 oxidation number. Hydrogen is going to equal its +1 charge because it has a charge of +1. Zinc is a +2 on the right-hand side of the arrow, and hydrogen, because it's elemental, hydrogen gas is 0. So the zinc has gone from 0 to +2, so that means it's been oxidized. The hydrogen has gone from +1 to 0, which means it's been reduced. All right, so that's the first. So this reaction is simple to balance because there's no other elements besides zinc and hydrogen. So let's split the half reactions so we can see it more clearly. So zinc goes to zinc 2 plus, and this is oxidation, which means and to balance this we need to have 2 electrons. Zinc has lost 2 electrons, so we put 2 electrons on the right hand side of the equation. Hydrogen, H plus, goes to H2. That's reduction. The first thing we have to do is balance out the equation by putting a 2 in front of the hydrogen. And now, in order to balance the charges, we have 0 on the right and +2 on the left. We have to add 2 electrons to the left-hand side. Now we can see that this, we can add these back together. The number of electrons are the same, but the oxidation, we're losing 2 electrons, we're gaining 2 electrons, so we can cancel those out, and here we have our overall balanced equation. All right, so let's look at another example. Copper plus NO3 negative, the nitrate ion, becomes copper ion, copper 2 plus ion, plus NH4 plus ion. So if we first do some inspection and look at oxidation numbers, we can see that copper has a 0 oxidation number on the left because it has no charge. Now we have to do a little more digging. So oxygen is almost always a -2 unless it counteracts something else, but we don't have a rule for N, so we're going to assume oxygen is a -2. There's 3 of them, so overall the oxygen is a -6. The total has to equal -1 because that's the charge of the ion. So nitrogen has to be a +5 to balance that out. Okay, on the right-hand side, copper is 2 plus, so because it's a 2 plus ion. And then again, we're going to have to do some digging. So hydrogen is a +1 in most compounds. So overall, the positive charge is 4. The total has to equal 1, +1, so nitrogen has to be a -3 to balance that out. So we can see that copper has been oxidized from 0 to +2, and nitrogen has been reduced from 5 to -3. But now, besides that, you can clearly see the reaction is not balanced because we don't even have any oxygen on the right or nitrogen on the left. So we're going to have to do a few more things to get this reaction balanced. And we also need to know if the reaction happens in an acidic or basic solution. All right, so these are the rules that you need to follow for balancing redox reactions in acidic solution. Okay, so the first thing you want to do, which we've already done, is assign oxidation numbers to each atom so you know what's being oxidized and what's being reduced. Then we're going to split the skeleton equations into the 2 half reactions, the oxidation half reaction and the reduction half reaction. Then we're going to complete each half reaction by balancing them and completing them. So how do we do that? First, we balance all atoms except for O and H. Then we balance all the O atoms by adding H2Os to the side where we need to put oxygens, but we're going to do that by adding water molecules. Then we're going to balance the H's by adding H plus ions to the side that needs hydrogen. And then finally, we're going to balance the electrical charge by adding electrons to the side that's more positive to get the charges of each side to be equal. Then what we need to do is combine the 2 half reactions to get the final balanced reaction. However, we have to make sure that that the number of electrons are the same the total number being oxidized and the total number being reduced. So what we're going to have to do, we might have to multiply each half reaction by a factor to get the total number of electrons to be equal within the two half reactions. And then finally, we can add the two half reactions together and look to see if anything shows up on both sides that can be reduced down. So we're going to do a couple of examples so you'll see what I'm talking about. All right, so let's balance the last example going step by step. So the first thing we've already done, we've already assigned oxidation numbers. Now we're going to split the reaction into the half reactions. So copper has gone from copper solid to copper 2+, that was oxidation. And the nitrogen has gone from NO3 negative to NH4+, that's reduction. That's our skeleton half reaction. So next, we're going to balance each half reaction. It really is you really should follow these guidelines to the letter. You really should go in the same exact order that I have them listed. So the first thing you should do is balance anything that's not an O or an H. So we're already good there because we have one copper on each side of the first half reaction, and we have one nitrogen on each side of the second half reaction. Then we're going to add O's. We're going to balance the O's by adding water molecules to the opposite side. So we can see in this second equation, we have NO3 negative on the left-hand side, so we have 3 O's. We want to get 3 O's on the right-hand side, so the way we're going to do that is to add 3 water molecules. O's aren't hanging around by themselves, and we're in an aqueous solution, so there's plenty of water around, and so the best way to add oxygen is to add a water molecule, and since we need 3 oxygen, we add 3 water molecules. The next thing we're going to do is add H's. But since this is an acidic solution, the H's that are hanging around are going to be H+ ions. So notice that in the second equation when we added the waters, we added 6 hydrogen, and that's why you should always do the water before the hydrogen because you're adding hydrogen always. So we've got 6 hydrogen on the right. And then we have 4 more attached to the end, so we have a total of 10 hydrogen on the right, so we're going to add 10 H+ on the left to balance those out. Now, the next thing we have to do is balance the charges by adding electrons. So now we already know that copper is being oxidized, so that means a loss of electrons, so that means the electrons go on the right-hand side. But if you didn't remember that, you can still do the process because you just want the charges to be the same on both sides. And remember that electrons are negative. So before adding the electrons, you could see that copper is a 0 and then Cu2+ on the right. How do we get these to be equal by adding negative charges? Well, we have to add 2 negative charges on the right-hand side. That gives us a 0 on the right-hand side, and we have 0 on the left. So we had to add 2 electrons to the right-hand side. Now, on the second equation, it's a little more complicated. So let's look before the electrons were added. We have a +1 charge on the right-hand side. So water is 0. NH4 is +1. There's only one of them. So the total charge on the right-hand side is +1. The total charge on the left-hand side, we've got 10H+. And then we have a -1. So before adding electrons, we have a +9. So +9 on the left, +1 on the right. How can we balance them? We have to add 8 electrons to the left because a +9 minus 8 gives us a +1. So now with the electrons added, we have a +1 on the left and a +1 on the right. So we've added the correct number of electrons. Again, you're always adding electrons to the more positive side to get the two sides aligned, the charges the same on both sides. Now, the next thing we have to do is multiply each half reaction by an integer to get the number of electrons to be equal between the two half reactions. So in this case, we see that copper going to copper 2+ gives off 2 electrons. However, we need 8 electrons for the second half reaction. So somehow we're going to have to get 8 electrons on the right-hand side. We have 8 on the left-hand side. So to do that, we're going to have to multiply by 4. All right, so if we take that, we have to, and to multiply by 4, we have to multiply the whole equation by 4. So that means we have 4 copper solid gives us 4 copper ions plus 8 electrons. So 8 electrons have been given off if 4 coppers are oxidized. The second one already has 8, so we don't have to change it. Every once in a while, often you only have to change one or the other. Sometimes you'll have to find the least common multiple and you'll have to multiply them both by some factor. But you always want the same number. So now we have 8 electrons on both sides that can be canceled. We don't want electrons showing up in the overall equation. So now we can add the half reactions together. So write everything, and it doesn't matter what order you write them in. Everything that's on the left-hand side of the arrow, we write on the left-hand side. So we have 4 copper plus NO3 negative plus 10H plus 8 electrons. Everything on the right-hand side of the arrow goes on the right-hand side. So we have 4 Cu2 plus NH4 plus 3H2O plus 8 electrons. Now we can cancel anything that shows up on both sides. So the electrons will cancel. So they'll go away. And here is our final answer. So this is the balanced oxidation reduction reaction given the skeleton half reactions that we looked at the beginning. All right, so let's do another example. Oh yeah, double check that the number of atoms and charges are the same on both sides, just to make sure that you've done it right. So we can do that. On the left-hand side, we have a total charge of -1 plus 10, so positive 9. On the right-hand side, we have 4 coppers. Each of those are a plus 2, so that's a plus 8, and then we have one more positive charge on the NH4, so we have a total of plus 9 on the right hand side. So our charges are balanced, and we have 4 coppers, we have 1 nitrogen, we have 3 oxygen, and we have 10 hydrogen on both sides. So we're balanced. I mean, that was the whole purpose, but just it's good to double check because it's so easy to make mistakes. All right, so let's do this example. Fe2 plus MnO4 negative gives us Fe3 plus Mn2 plus. So the first thing we want to do is get the oxidation number. So it's easy. Fe2 plus is a plus 2. Fe3 plus is a plus 3. Mn2 plus is a plus 2. But we're going to have to figure out what Mn is on the left. So the total charge is a -1. There's 4 oxygens, which are each -2. So what do you add to -8 to give us -1? You have to add a positive 7. So Mn is a positive 7. So clearly, iron has gone from plus 2 to plus 3. So that's oxidation, and I've pulled that out as my half reaction. And then MnO4 negative has gone from plus 7 to plus 2. That's a reduction. So I've pulled those out as my other half reaction. Now we want to balance each half reaction. So the first thing we want to do is actually balance everything that's not H2O or H+. So that was already done. Fe, there's 1 Fe on each side. There's 1 Mn on both sides. Now we have to balance by adding H2O. So we did that. There's 4 O's on the left-hand side, so we have to add 4 H2O's on the right. Now that we've done that, we have 8 H's on the right, so we have to add 8 H pluses on the left. Then the next thing we have to do is add our electrons. All right, so Fe2 plus and 3 plus, we have to add 1 electron to the right to balance those charges. So now both sides are plus 2. On the left-hand side, let's see, before adding the electrons, we have a positive 2 on the right-hand side, and we have a positive 8 and a -1, so a positive 7 on the left-hand side. So we have to add 5 electrons to get them both to be positive 2. So we've added 5 electrons. The next thing we have to do is make sure our electrons are the same in the 2 equations. So we're going to have to multiply that first equation by 5. When we do that, we get 5 Fe2 plus gives us 5 Fe3 plus 5 electrons. Now the electrons are the same on both sides, so we can add the 2 equations together. 8H plus 5 Fe2 plus MnO4 negative plus 5 electrons gives us 5 Fe3 plus Mn2 plus 4 H2O plus 5 electrons on the right hand side. Then we cancel like species, which are the electrons. So here is our balanced equation. And then just double check. So on the left hand side we have a positive 8 and a positive 10. That's a positive 18 minus 1 means we have a positive 17. How about on the right? We have 5 times 3 is a positive 15 plus 2 more is a positive 17. So the charges are balanced on both sides. And we have 5 irons, 8 hydrogen, 2 Mn, 1 Mn, and 4 oxygen on each side. Now, what if we were doing the reaction in a basic solution? There's a few more steps that you have to do. It's usually best to start by balancing it with pretending you have an acidic solution, and then do this at the very end to fix it for a basic solution. So what happens if you have if you have hydrogens hanging around and it's in a basic solution? Those hydrogens are immediately going to react with OH negatives to react to give us a water molecule. So what we're going to do is add OH negatives to both sides. Because we already have a balanced equation, we're going to add OH negative to both sides of the equation. The number is going to be equal to whatever the H plus is. So let's say we had 5 H plus on the left, we're going to add 5 OH negative on the left. And then we're going to keep it balanced, add 5 OH negative on the right. Now what happens is, though, on the left hand side, 5 H pluses plus 5 OH negatives combine to give us 5 waters. So we're going to rewrite the OH and H pluses as waters. And then finally you just cancel H2Os because they'll end up showing up on both sides, so you can cancel them out, whichever one you have more of. So let's do an example using this method just to see how to do that. All right, so let's balance the following redox reaction in a basic solution. However, I highly recommend just doing it as we've already been doing it for acidic solution, and then do the final correction at the end. So the first thing we want to do is find out what's being oxidized and what's being reduced. Actually, it's probably pretty straightforward. Here we know the ClO is going to Cl2 and the Br negative is going to Br2, and so we can actually split those into the 2 half reactions. But let's just see what's happening beforehand, because it's sort of, when you're making, you can make so many easy mistakes. So in this case, the Br negative going to Br2 is going from -1 to 0, so that's oxidation. The Cl on the left hand side, if the O is a -2 and the total is a -1, Cl has to be a +1. So it's going from +1 to 0 on the right hand side, and so that's being reduced. So we have our reduction half reaction, ClO negative going to Cl2. And the reason why I like to check that out with my oxidation numbers is because since this is reduction, we need to have the electrons on the left hand side, and then the Br negative going to Br2, our electrons are going to have to end up on the right hand side. So you can catch yourself if you make mistakes along the way, because you know what to expect. Anyway, we have our 2 half reactions, and the first thing we should always do is balance the half reactions, balance everything except O's or H's. So we have to put a 2 in front of the ClO negative. Now we're going to balance the O's by adding 2 H2Os on the right hand side. And then because we've added 4 H2s on the right hand side, we're going to add 4 H pluses on the left hand side. So we've totally balanced everything except the O's and H's. And then we add water to balance the O's and H pluses to balance the H's. Look at the second equation. All we had to do was put a 2 in front of the Br negative to balance the Brs. And we had no O's or H's, so we're good there. The next thing we want to do is add electrons to balance the charges. So notice in the second equation on the top, we have a -2 because we have 2 ClO negative, and we have a +4. So overall, the left hand side of the equation is a +2. The right-hand side of the equation is 0. So that means we have to add 2 electrons to the left-hand side to get them both to be 0. So now we have -2 plus 4, -2, total of 0. In the second equation, because we have a -2 on the left-hand side, we have to add 2 electrons to the right-hand side. So now both sides are -2. It doesn't matter what the charges are, they just have to be the same, and we have to add enough electrons to make them the same. And then just another common mistake, at this point, if you're putting electrons on the same side of the arrow, you've done something wrong. The reduction should always have them on the left, and the oxidation should always have them on the right. So you've probably made some mistake along the way if it turns out you're trying to add them on the same side. So now we have our 2 half reactions, and luckily they both have the same number of electrons, so we don't have to do any multiplying. So we write everything on the left-hand side of the arrow, everything on the right-hand side. Since the 2 electrons are the same, we didn't have to multiply by any factor. So we can cross the electrons out, and we have this equation. 2ClO negative plus 4H plus gives us plus 2Br negative gives us Cl2 plus 2H2O plus Br2. Now, this would be a perfectly good answer if this solution was happening, if this reaction was happening in an acidic solution. But because it's happening in a basic solution, those 4 hydrogens are not going to be just hanging around trying to make this reaction go. So what we're going to do, because we have 4 H pluses on the left, we're going to add 4 OH negatives to both sides. So you can see here 4H plus on the left. So we're going to add 4 OH negative on the left. To keep it balanced, we're going to add 4 OH negative on the right. Now, on the left, the 4H plus 4H negative are not going to hang out. They're going to react. So they're going to form water. So 4H plus 4OH negative give us 4 water. So now we have this reaction. The OH negatives on the right have to stay because they don't have hydrogen to react with. And then finally, you can see that we have 4 H2Os on the left, 2 H2Os on the right, so we're going to just reduce that down. So take 2 away from the right and we'll cancel all those out. Take 2 away from the left and we'll have 2. So our final reaction is 2ClO negative plus 2H2O plus 2Br negatives gives us Cl2 plus 4OH negative plus Br2. So if you have a basic solution, you can only have OH negative hanging out and not any H pluses. So just a couple of things to remember. Don't forget to balance elements besides H and O before you get started. Add the correct number of H2Os. Then add the correct number of H pluses. Then balance the electrons for each half reaction. Then you're going to have to multiply it by a factor to get the electrons to be the same in the 2 equations. And then finally cancel out anything that shows up on both sides.